Hello, my name is Jurnam Yapara, and my project team members are Aisha and Favor. And today our project question was number 4. An oil spills on water can be removed by lowering a moving belt of width W into the water. The belt moves upwards and skims the oil into a reservoir aboard the ship, as shown in the figure below. So this is the figure. So we were trying to figure out show the velocity profile, velocity profile and volumetric flow rate as given by these two equations. And part B, we were trying to determine the belt speed that will give a 0 volumetric flow rate and specify the different criteria for positive and negative flow rate.
So this is our diagram for the problem 4. So we got our oil here, and the oil is moving downwards while the belt is moving in the opposite direction. So this is the velocity profile. So since there is two moving fluids, so it will be in the opposite direction. So the one fluid will move this way and the other will move the other way, and at the angle beta 2. And this is also our momentum profile. So according to, so those are,
So in this question, we came up with a few assumptions. So first, we're assuming that it's a steady state. There's a flow due to gravity, one component velocity, Vz, neglecting any end effects, Newtonian fluid, incompressible flow, and no velocity gradient of fluid air interfere. So we have the momentum balance.
so our momentum balance is rate of momentum in minus rate of momentum out plus the sum of forces, which is equal to 0. So here our molecular, our transport molecular balance will be the tau at x is equals at tau at I mean where the fluid is flowing in the z direction into the x at x minus tau at x plus delta x times the area, which is the length times the width. And our convective transport is 0 because it is we are assuming it's steady state. And here we are only the gravity as a force, which is rho g cosine beta times the area, which is the length times the width times the delta x. So when we rearrange or when we combine all these equations, we get the tau at x minus the tau at x plus delta x plus the force, which is rho g cosine beta times the area, and here 2 times the area, which is equal to 0. And here we can see that this is the differential. So this is initial minus final. So that's why here it becomes negative. So that's negative the differential of tau over dx, which is equal to force. So from here we can solve for tau, where we have to put the integral and then do the math. And then here we have this equation and we got C1. And then how to get C1, we have to add our boundary condition. And then our first boundary condition will be at x, like at the very beginning, x is equal to 0, tau will also be equal to 0, and C1 will also be equal to 0. So from that we can say that tau is equal rho g cosine beta.
Okay, and so for our second boundary condition to find our second constant, we set x equal to delta. And so whenever x is equal to delta, that is whenever x is like the fluid is touching the moving belt. And so we know whenever x is equal to delta, our velocity is going to equal negative velocity because the belt is moving in the opposite direction of our axis. And so we get negative v is equal to negative rho g cosine beta delta squared over 2 mu plus our constant. And so moving the rho g cosine beta delta squared over 2 mu to the left side of the equation, we get our constant. And then we plug that constant back into our velocity equation. to get rho g delta squared cosine beta cosine beta delta squared over 2 mu, or rho g delta squared cosine beta over 2 mu times 1 minus x over delta squared minus velocity. And so to find our average velocity, which we need to find the second part of the first, to find the volumetric flow rate, we have to find our average velocity. And so we are able to find that using this equation, and we get our average velocity as rho g delta squared cosine beta over 3 mu minus v. And so we multiply that by our cross-sectional area to get the volumetric flow rate. And our cross-sectional area is delta times our width. And so we get our volumetric flow rate as W rho g delta cubed cosine beta over 3 mu minus our width times velocity times delta.
So from there on, we were trying to determine some criteria on what makes Q equals to 0. So we were given that Q is equal to 0. So which therefore that the width and the velocity is the integral of the width rho g thickness cube cos beta over 3 mu. So which therefore that the velocity, which equals rho g thickness cubed cos sine beta cosine b over 3 mu. So in order to determine if we have a Q of positive or negative, so if the V is less than this equation, that means it's a positive. Or otherwise, if the velocity is greater than this equation, that Q is negative. So in terms of the actual physical diagram, we can have different angle inclines, which affects the flow rate. We have the different types of fluid. We can have oil, we can have water, whichever fluid. And in general, if air is involved, we can have a reaction, different types of reaction, and as well as the moving belt, sometimes there's forces acting on top of the belt. So that includes our project 1. Thank you.